we're going to start by talking about resistive temperature sensors. All right. We did a little thought exercise last time where we imagined that there is a resistor and has a certain resistance, but that resistance is a function of temperature. So for example, if the temperature was 25 degrees, perhaps it has a resistance of 1 ohm. If the temperature is 30 degrees, it has a resistance of 2 ohms. Now this is a very bad resistor if you are just making a circuit, right? Because you're building a circuit, you want it to behave a certain way. You don't want, the temperature in the room to go up and suddenly your circuit doesn't work that way. But this is the basis for how we're going to make devices that measure temperature based on resistive temperature sensors. So it starts right here. Now, there's a specific kind of temperature sensitive resistor that is called a thermoresistor. And with a thermoresistor, the resistance is a function of temperature given by the equation R sub 0 times 1 plus alpha times temperature T minus temperature 0. Okay. Let's go through each one of these terms. This is the resistance at any given time, all right? This resistance changes, right, with temperature. And that temperature is given by T sub T. Maybe that's a peculiar notation, right? So this resistance changes, right? You can see that this resistance depends, among other things, on this temperature, right? If this temperature goes up, so will this resistance. R sub 0 is the resistance at temperature T sub 0. For example, it may be the case that at 25 degrees, right, the resistance is 1 ohm. And so that would be plugged into here and here. And finally, alpha is the temperature coefficient of resistivity. So we'll call it the temperature coefficient of resistivity. Okay. There's quite a few terms here, right? But it's not a complicated equation because, in fact, there is simply a relationship between the temperature and the resistance, and all these are just parameters. They're constants, right? So you can imagine you can plug in 10 here, 1 here, 25 here, right? And we have a very simple linear equation. Okay, you'll say, but where do these values come from? They come from the type of thermoresistor that you buy. So when you buy a thermoresistor, or when you are given a thermoresistor, the R sub 0, the T sub 0, and the alpha are specifications of each model. So just like when you buy a computer, you're looking at the memory and you're looking at the processor. Those are just things you're looking at when you're trying to pick one. These are the specifications that come with your thermoresistor. So when you buy the thermoresistor, it'll come with a little piece of paper, and the piece of paper will say, This is the temperature coefficient of resistivity. This is the R sub 0, and this is T sub 0. And from that, you have all the information that you need, right? So if, for example, it had the values of alpha equals 1 and T sub 0 equals, well, we'll use that example, 25 degrees with an R sub 0, using the same example, equal to 1 ohm, then we will have a situation where R sub T is equal to 1 times 1 plus still 1, so very simple, temperature from T minus 25 degrees C. And there we have it. Now, these units here, for the units to work out, these units are going to be in ohms. These units are going to be in ohms. These units here are both in degrees C. And so the temperature coefficient of resistivity has to be in ohms per degrees C. Right? So to be clear, this was 1 ohm per degree C for the units to work out. And so now we have here a pretty simple equation. You can go ahead, if you want, you can simplify it, obviously. You can cancel out, you can just wipe out this 1 and wipe out this 1. And you have a clear relationship between RT and temperature. And that relationship for a thermoresistor looks like a straight line. Right? If we set here as T sub 0, then we will start with R sub 0, and as the temperature goes up, so will the resistance. And this here has a slope of alpha. So for any temperature, let's say we talk about 30 degrees C, 31 degrees C, for every temperature, we have an associated resistance. But very important for our purposes, for every resistance, we have an associated temperature. Now, you wouldn't have that if you didn't have an equation with parameters. It had to have an equation. It had to have parameters, right? If I didn't give you the equation, well, you wouldn't know the relationship between the resistance and the temperature. Or if I had given you the equations, but I had left out these parameters, you once again wouldn't have that information. So the equation and the parameters define this relationship, which is essential for the usability of this device. Okay. And so now we have, let's imagine that this is our thermoresistor, right? And there we have it, right? We have our thermoresistor, and we know that it's going to be a certain resistance now because it's in the air. And if your little brother grabs onto it, right, his body heat will heat up the thermoresistor, and therefore the resistance will change. Great. But how do we convert that into an instrument? Right? I mean, him just grabbing onto it, well, unless no one has the ability to look, right, at a resistor and know what its resistance is. So the thermoresistor, right, is the first component. It is the sensor, right? But we're now going to need to use a circuit, right, in order to convert this resistance, right, into something more usable for our purposes. Okay? It is a simple circuit. And so the next thing I want to cover is a circuit called a voltage divider.